Hi everyone, welcome back to the online tutor. So today I'm going to discuss the mathematical induction lesson. So also I had to tell you, so this question is nowadays it's coming from the structure essay paper, right? But this mathematical induction and the series question is a little bit connected, right? So because the some properties in the series can be proved using mathematical induction. Okay, but anyway, you should need to understand what is this mathematical induction is. So the mathematical inductions, in our mathematics, we have so many statements, we have so many equations, right? So mathematical statement or equations can be proved by using mathematical induction, right? So we have to show this statement is true. So the mathematical induction is the way of proving this statement. So assume if you have some inequality, right? You have to prove this inequality is correct for some positive integers. So the mathematical induction is the way of proving. So if you have a algebraic expression like trigonometric equations, right? So we can prove this trigonometric equation using mathematical induction, right? So other so part of that, if you have a integration statement, you have a differentiation equation, so something like that, you can prove this statement is true, right? So actually in mathematical induction we have a mechanism, right? So you should need to go through this mechanism. So you have to understand, we have to understand the process first, right? So because you can't write in your way, right? So in mathematical induction we have a well mannered method, right? Implement method to prove something, right? So that first of all you should understand the principle of the mathematical induction, right? Okay. Mathematical induction is a one of the technique which can use to prove variety of mathematical statement which are formulated in terms of n, where n is a positive integer, right? So you can't prove this state mathematical induction for a rational numbers, for the irrational numbers, for the real numbers. It works only for the positive integers. That is the first main thing you should understand. Your statement should be given in terms of n. N is a positive integer only, right? And also in our advanced level syllabus, right, we have only actually these days we have only two cases, right? So you can see now the types of mathematical induction problems. So first one is divisibility cases, second one summation cases, third one inequalities, last one the others method, that's trigonometric integrations, differentiation, algebra, complex numbers, and something like that, etc dot dot. So we can prove this all, right? But nowadays in our examination only the divisibility cases and the summation cases are coming, right, uh, through the structure is a question, right? Actually these two is the only questions that they ask nowadays. But some lessons in some complex numbers theory parts are proved using mathematical induction, right? So we can use the mathematical induction for proving some theory parts, a part of the some few algebraic lessons, right? Okay. Okay, let's see what is this principle of mathematical induction. Let Fn be a given statement involving the natural number n such that the statement is true for n equal 1. Either F1 is true or else any fixed natural number. So like that, the row number 1 is including the first step, right? So you have to prove this for n equal 1, n equal 1 or n equal 2 or any true, any fixed natural number, right? So normally we are doing for n equal 1 actually, right? The second step, if the statement is true for n equal p, where p is a particular but arbitrary natural number, then the statement is also true for n equal p plus 1. Either truth of n equal p, like fp, implies the truth of fp plus 1, then fp implies the truth of fp plus 1 mean it's true for all natural integers, right? So the second step words, you can assume some fixed point, right? You can assume some particular point n equal p, right? P is including any number 10, 50, 20, 100, anyone, right? So you can assume n equal p is true, right? Then after you have to show this n equal p plus 1. So p plus 1 mean the next position. So the p and p plus 1 are the consecutive numbers, no, p and p plus 1. So next integer, now integer. So you have to prove this n equal p plus 1 is true. That means your statement will, if it is true, I mean n equal p plus 1 is true, your whole system is true, right? So that is our mathematical induction principle. So what you have to do, first you have to show n equal 1 or any fixed integer is true, and second thing, you have to assume n equal p is true for any a natural number, and the next thing you have to show n equal p plus 1 will be true. If it is true, your statement is completely true for using mathematical induction. If the n equal p plus 1 is not true, it's not, the whole system, whole equation will not be true. So that is the mechanism of the mathematical induction, the principle of the mathematical induction, right? So after that, what you have to do, you should write down the final conclusion. So you can write, so for all in natural numbers this works, this is true, this statement is true, this summation is true, this inequality is true. Likewise you can include, you can mention your some, sorry, you can mention your conclusion, right? So the as a last step, right? Okay, this is the principle of mathematical induction. Okay, let's look at
Right.
a example in mathematical induction. So first, I'm going to discuss the first type, the divisibility cases using mathematical induction. Right. So now you can see the screen, the question number one, divisibility cases. Right. Using mathematical induction, using mathematical induction, through that 10 to the power n minus 1 is divisible by, is divisible by 9. Here n is a positive integer, right? So you can see whatever you put for n, so we have to show, I mean it's only the positive integers, so whatever you put as a positive integer, it should be divisible by 9. So actually you can see, it's when you put n equal 1, it's 9, is 9 is divisible by 1, and when you put n equal 2, it's 100 minus 1, it's 99, likewise. So it's true, but we can't say it like, no, we can't say like it like that way. You have to prove using mathematical induction. In mathematical induction we have a principle, right, to prove something. Let's look at how to prove using mathematical induction. So can you remember the first step, the step number one? It was, we have to prove when n equal 1 is true. You have to show n equal 1 is true. So what you have to do, you should substitute n equal 1 first. 10 to the power 1 minus 1. You know it's 9. 9 mean 9 into the 1. So 9 is divisible by 9. So therefore n equal 1 is true. So our first step is already true now. So any arbitrary number, right? Any fixed natural number, you have to show it's true. Right. So the step number two, can you remember it? We have to assume n equal p. P is any positive integer, right? The statement is true. That means fp, our function fp, we assume that n equal p is true. Fp 10 to the power p minus 1 is 9k. So 9k mean it's divisible by 9 anyway. It's 9 something. 9 some positive integer. 9k. K is a integer. 9k. So because we assume 10p minus 1 is divisible by 9. When it's divided by 9, it will be, the answer will be an integer. No? That's why I put k. So step number 3, we have to show when n equal p plus 1 is true. N equal p plus 1 is true mean this is what we have to show. N equal p plus 1 is true. So now you can put n as p plus 1 and simplified it. 10p plus 1. If p plus 1, 10p plus 1 minus 1. 10p plus 1 means 10 into 10p using our indices knowledge. 10p is using our previous step. 10p is 9k plus 1. Now you can substitute it to the main equation. 10 9k plus 1. 90k plus 10 minus 1. 90k plus 1. 90k plus 9 now. 90k plus 9. 9 can be taken out. It's 10k plus 1. 10k plus k is an integer, no? So 10k plus 1 should be another integer. It's like k dash. It's 9k dash. 9k dash means it's divisible by 9. Right? So k dash is integer. And therefore, we prove n equal p plus 1 is also true. N equal p plus 1 is true. N equal p plus 1 is true. Right. So the step number 3 is also over. Next step, step number 4, you have to state your conclusions. What is the conclusions? So anyway, we prove n equal 1 is true. And n equal p was assumed that is true. And here now n equal p plus 1 also true. Therefore, for all integers the statement is true. N equal 1 is true, and we assume n equal p is true, and n equal p plus 1 is also true, right? So then therefore for all positive integers this statement is true. 10n minus 1 is divisible by 9. This is our final conclusion. So you should state these all steps, right? Okay, let's look at another example. Question number 2. Using mathematical induction, prove that 5 2n minus 1 is divisible by 24. It's divisible by 24. Right. So this is my fn 5 2n minus 1. So what was the first step? N equal 1. We have to prove n equal 1 is true. Yeah, you can see it's 24. It's divisible by 24. Next one, n equal p, we assume is true. So we assume it's true. 5 to the power 2p minus 1 is divisible by 24. It's 24k. K is an integer. And the next step was n equal p plus 1 will be true. So you have to show this will be true. So I'm going to simplify it like 2p minus plus 2 minus 1, and we can write pi to the power 5 2 like 25. 25 into phi 2p minus 1. Phi 2p can be replaced by 24k plus 1. You can see there's a pattern now. Comparing with the last question, first question, same. 25 into 24k plus 25 minus 1. Minus 1 can 24. 24 can be taken out. 25k plus 1. This is k dash. 24k dash, that is exactly divisible by 24. Therefore, n equal p plus 1 is also true. So the next thing is you should write the conclusions. N equal 1 is true. We assume n equal p is first true. And now n equal p plus 1 also true. Therefore, for all positive integers, 5 to n minus 1 is divisible by 24. So that means all the time you have to go through these steps. And it works for all n positive integers, right? Not for the rational numbers, not for the irrational numbers, not for the real numbers. Only work for natural numbers. Right. So these are my questions. Next questions, third, fourth, fifth, sixth. You can try it now, right? Please, I hope you all write in my theory parts, right? And so actually this video is made including the theory parts and all, right? So you can start from a book and write down all. Okay, let's look at third example. 6n minus 5n plus 4 is divisible by 4. You have to show this n equal 1 is true. So I got 5 is divisible by 5. N equal 1 is true. And next n equal p, we assume it's going to be true. And n equal p plus 1, we are going to simplify it as the previous one. I'm going to substitute n like p plus 1, no? 6p equal 5k plus 5p minus 4. So I'm going to substitute from there. Sometimes you feel I'm going really fast. No, it's not fast. Same thing, no? Same thing happening, right? So n equal 1 true, n equal p we assume, and we subject that property from the first n equal p, and I'm going to substitute n equal p plus 1 and going to simplify it. So that final answer should be divisible by 5. That means 5 terms should be outside the bracket. This is k dash. 5k dash. 5k dash mean is divisible by 5. Right, so now n equal p plus 1 is true. So next you have to state the conclusion. I didn't write the conclusions because the last two questions we brought it. It's up to you to complete. Right, so okay, this is third example and I put some examples, right? So I think you have seen it. Fourth, fifth, sixth, seventh questions, right? So you can try it now as a homework. So next tutorial, I'm going to discuss this fourth and fifth, sixth, seven, all, right? So I think now you are okay with the mathematical induction basic and the proving divisibility cases, right? So the next tutorial, I'm also going to discuss the homework question and going to start the next part, the divisibility, the summation cases using mathematical induction. So thank you very much for watching the video and don't forget to subscribe my channel and have a nice day. Bye bye.